Biostat 6611, skills for the rest of your life. Bootstraps and probability. It's the bread and butter, baby. What's your jam?
Good day, Bio 6611. In this lecture, we're going to discuss the idea of simulation studies. We're going to first discuss what is a simulation and why would we want to simulate data. We'll then introduce an example, briefly touch on reproducibility, and also talk about the distribution of the sample versus the population. So let's start off with discussing what is simulation. Now, this is one of the most useful and powerful tools we have at our disposal with modern computation. A simulation is something that will mimic what we call the data generating process. For example, we generate samples from some known distribution, like a normal distribution. And again, the distribution is that mathematical depiction or representation of our data using things like a normal, exponential, Poisson, gamma, or so on distribution. Now, since we sample from a known distribution that we choose or we set as the truth, we can then actually use this to say, well, if this actually was the truth in the population, how would my results or my conclusions work with a given test, estimator, or property? Now, within any given single simulation, we'll generate a sample of size n observations from our chosen distribution, and we'll see this play out in some examples. We then repeat this process of our simulation many times over to estimate things, again, like our chosen model, an estimator, some new algorithmic approach, or anything else we might have questions about to evaluate the performance and properties of. So why simulate? Well, much of statistical theory, which is a different course unto itself, is based on what we call asymptotic approaches. In other words, as n gets really big and goes to infinity, what would we expect the properties of our test or our statistic to be? And these are often based on assumptions. For example, we assume maybe normality to do certain statistical tests. Now, the challenge we have in practice, because we don't get to live in this theoretical world, but we in fact live in the real world, is that we have finite samples and assumptions may be violated. And we may wonder, well, how violated of our assumptions is too much, or how small or finite of a sample doesn't make it challenging or maybe inappropriate to use certain approaches. Well, if we know the truth, which we can't in reality, which is why we do research and take samples, we could then actually evaluate how well different statistical methods would work in a given context. Which in fact here we could actually simulate that data by assuming some known truth. For example, we could assess multiple estimators like we discussed with the criteria in the Properties of Estimators lecture. And we could do so under different scenarios with maybe different sample sizes or different types of underlying distributions to address questions about, well, what would happen in a given scenario if I happened to encounter it? So with that sort of motivating features in our mind, let's take a look at an example. Let's start with the simulation example, assuming we have a normal distribution. And here we will think of the height of all women in America as following a normal distribution, where we'll say they have an average or mean height of 161 centimeters, and that we've calculated the standard deviation to be 5 centimeters. Now, one quick note, to simulate we either need to know or assume the distribution we want to sample from and its parameters. So here we might say that this little graphic we have from the CDC data looks vaguely normal-ish, or normal enough that we might be comfortable assuming a normal distribution for our simulation. Let's take a look at how we can simulate one sample of size 6 from that distribution on the previous slide using the rnorm function in R. Now, let's first break down the arguments of this function. So what it's doing is generating randomly simulated normal observations. Now in our case, it's going to take our sample size of 6, because that's what we are telling R to do, and we'll then specify these additional arguments for the mean and standard deviation that we're assuming or proposing from the previous slide, that the mean height of women is 161 centimeters and that the standard deviation is 5. Now we see in the output of this one sample we have 6 observations, and we see that the values are in the ballpark of 161, but they're kind of all over the place. Now, this is just one sample of 6 observations, and we could imagine repeating this many times over. But before we can get to that component or that piece, we need to add one very important part to this chunk of code. And this brings us to the idea, an important concept of reproducibility. So let's stop what we were doing before and say that we walk away from that simulation problem, but 3 months from now we want to replicate that exact same sample we saw on the slide with those 6 observations. What we currently have would not be reproducible because we haven't actually told R any benchmark or starting point to use. Instead, what we need to do is to set the seed. We need to plant a good garden of reproducibility by telling R where do we want to start the simulation from. Now, the seed is that initial value we use in our random number generation. So using different seeds will lead to slightly different or very different samples. Now, if we don't set the seed, R does have a default way of approaching that problem by generating its own sort of starting point based on the current time and date. Now, for reproducibility reasons, obviously, it's important to set the seed so that others, including future you, can replicate your results and come to the same conclusions. Now let's return to our R code example, but first we'll set the seed and we'll expand this to generate 10 simulations, each with a sample size of 6. Now in this simulation we're going to calculate the mean or the sample mean of each sample, and we'll do so in a vector called thetas. Now we can see that in our code down below here. We're creating this object thetas to be 10 long, a vector of 10 NAs to be replaced with our observations on the next slide. One important thing to note with setting the seed that we see here at the top of our code chunk is that we want to set it outside of the loop we're going to use on the next slide or whatever function we use. If we do it inside the process, we will just repeatedly set the same seed and generate 10 samples with the exact same points, having no variability, which would be very bad. So here we see an example with a for loop for our simulation, and it's this piece of code here within these curly brackets, this chunk of code. And so we can break down a few different pieces here. One is that we actually see the sample line of code from before is the exact same, but we're just looping through it for the number of reps, in this case 10. What we're then doing within each step is we're calculating the mean of the 6 observations we randomly sample or generate in that first line of code, and then we're going to save it in the spot of this ith location in our vector. Now there's lots of ways, and we'll discuss this in class more, that we can develop and set up for loops or do things computationally faster with things like apply statements that vectorize the approach. But we can note here that we've indexed this for loop to go from 1 up to the number of reps, and we circled that right now on the screen here. So it's essentially going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, simulating those 10 data sets. And so what we're doing here is we're telling R to extract the ith element and replace it with whatever the sample mean is from our simulation. Now, once we run this little for loop, we can see here we can print the thetas we have in our sample means, and we see that we have again 10 different observations that vary from one another, but seem to be a little more consistent or in the neighborhood than that one single sample of 6 observations. Now again, remember, each one of these is a sample mean with 6 observations, and so we have x bar 1, x bar 2, all the way up to the bottom here of x bar 10. So with this information, we can also start to discuss or think about the distribution of the sample versus the population. Again, getting to this distinction of that overarching population of interest versus the sample we take or observe. So we can note that none of those 10 samples had that exact sample mean, or population mean I should say, of 161. Those sample means varied a little bit around that neighborhood of values. And samples will usually look different from the population they're being sampled from, unless your sample covers almost the entire population or there's very little variability. Now, each random sample will be different from any other random sample we take, and we can identify this by, again, just generating those different random samples within R, or if we picture randomly selecting people from a population, we can imagine that while someone might be selected in multiple random samples by chance, they won't usually be in the same sample with the exact same other people who are sampled. So then each estimate we have from a random sample will vary slightly, but hopefully be within the neighborhood of what we're trying to estimate. We have this concept within statistics then of what we call sampling distributions. In other words, the collection of sample means we had from our previous example, or that vector of thetas, has its own distribution known as the sampling distribution of the statistic. So in our case, that's the sample mean. The sampling distribution of any statistic will rely on the underlying population distribution, the statistic being computed, and the sample size. For example, we had assumed that we had a normal population with the mean mu and a variance sigma squared. If we repeatedly take samples of size n from this population and we calculate the sample mean for each sample, we could then show that the sample distribution for the sample mean can be represented as still a normal distribution with the same mean, but the one piece that will differ is the variance will be sigma squared over n. And we'll see this more as we discuss the normal distribution in a few weeks. But this specific thing here, for x bar, we're saying it's distributed as a normal distribution with those population parameters that we're assuming to be true. So as a final example, let's just walk through a simulation where we actually assume that the population is distributed as an exponential distribution with a rate of 2. In other words, you might see this denoted in some places as exp with lambda equals 2. Now, if we do a little research into the exponential distribution, we can know that the mean of that distribution is equal to actually 1 over lambda, or in our case, 1/2 or 0.5. We can also plot the sampling distribution from our simulations to get an approximate empirical estimate of what that sampling distribution may look like. So instead of simulating just 10 sample simulated data sets, let's simulate 10,000. And here, instead of a for loop, we'll use the sapply statement. And in this case as well, instead of an observation or sample of 6, we'll use 25. So again, the first thing we want to do is set that seed outside of either the loop, the apply statement, or the function we're using for the simulation in order to have reproducible results. We'll then use the sapply statement to do 10,000 random samples, and again we're nesting functions within each other. So we have our REXP function, which will randomly simulate or generate 25 observations assuming a rate of 2 from the exponential distribution. We've then wrapped that within the mean function within R to calculate the mean of those 25 observations. What we can then do is from our 10,000 estimated sample mean vector, which we're calling here simres, we can calculate the mean of the 10,000 sample means. In other words, we see that that estimate is 0.4997321, or extremely close to the true underlying population value of 0.5. Now, as I mentioned, we can actually plot the sampling distribution from the simulation. So if we didn't know the theoretical sampling distribution, or we didn't have the ability to derive it, we could still get some idea of the empiric shape and properties from this graphical representation. And so here we're just plotting a histogram of, again, our vector of 10,000 sample means from those 10,000 simulated data sets with sample size 25 from the exponential distribution. And we're also just adding this AB line of code here to add the actual the mean of the sample means from the previous slide to our figure. And what we see here, given that sampling distribution we noted on the previous slide where x bar would be approximately normal with mean mu and sigma squared over n, we do see that even though our underlying data generating mechanisms for the x's are exponential, we do see that we still have an approximately normal distribution with maybe a bit of a longer right tail. So in summary, simulation generates data where we know the truth. Or in other words, an assumed population distribution that we are the ones making the assumption about as the truth. Now, what this assumption allows us to do is to evaluate how well different methods may work on that given truth. One thing, of course, that is important to note for reproducibility is to never forget setting the seed. And another important takeaway from this lecture was that the sampling distribution is that distribution of a given sample-based statistic, which can differ from the underlying population distribution we're assuming for the individual pieces of data, like we saw with the exponential distribution simulating a sample of size 25, whereas the sample mean itself still had a distribution that looked empirically to be approximately normal. We'll see these concepts come out throughout the rest of the semester as well as we get more experience playing around with the idea of simulation and seeing the different places and ways we can use it.